any address could go anywhere. That is the best utilization. That is what is called as fully associative memory. So what is done is that when the memory is accessed, so see, the beauty of direct map was you know which particular row to access, and you would compare only that cache tag with your address. But if any address can go anywhere, what happens? You now do not know which row is to be addressed. Now, any address could be anywhere. So any index could be anywhere. So my cache tag, I need to have a comparator for every line now. Are you able to see this? I need to have a comparator for every line now, and I will generate what is called as a match signal. And that match signal will be used to select the final address. So what kind of memory architecture are we talking about over here, where there are comparisons inside the memory itself, and then we give out the data? Are we talking about, are you still talking about SRAMs, or are we talking about something else now? Yes. So Kazi is saying we are now talking about content addressable memories. So based on what is the content in the cache tag, I decide to give which cache data to be given out to the processor. Are you able to see this? What is the disadvantage of this fully associative memory? The advantage we already talked about, that the total number of misses will reduce. What is the disadvantage?
Time required to compare, sir, increases.
So area penalty also, I think.
Yeah, even area penalty.
Time
Why
will be same, I think, because they'll be these comparators will I think compare the values in parallel, I think. So the area will be similar, like comparing a single comparator if it compares but I think we're using a lot of them here. So that's
So what we are saying is that area of this fully associative cache should be much higher than a regular cache that we talked about. Okay, what else?
So power also, I think.
Yeah, see, power also will be very high, because now instead of just comparing one word, you are comparing as many number of words as there are lines, as many number of tags as there are lines. So not only has the area increased because you need so many parallel comparators, now all those parallel comparators are also operational. They are consuming power. So this also increases. Overall, at the system level, the miss penalty reduces because the number of misses are fewer. Therefore, it may have a better overall effective access time, but at a huge cost of area and power. So can there be an intermediate way? The intermediate way is what we call as set associativity. So in fully associative, any address could go anywhere. In set associative, what I do is I define sets. That okay, there are these 4 sets. Now, if the last few bits of a particular address are 000, they do not have just one location to go to, as was the case for direct map. Now, we could go to 4 different locations. If it is, say, 4-way set associative, or n different locations if it is a n-way set associative. So this example over here is actually not 2, it is 4-way set associative cache. So what is happening? Oh, no, no, 2 here. Sorry. So what is happening? There's this one cache. There's this other cache. In both the places, we store cache tag, cache data, and so on. So now let us say the first row was to be addressed. So what do? We access both the memories, the first row, or let us say this row of both the memories. The tag is compared with the original address tag at both the sides. Okay, so again we have just one comparator now. We have no, not one. We have one comparator per way. Instead of one comparator per line, we now have one comparator per way. So our is a little more than direct mapped. Area is a little more than direct mapped. But now the miss penalty significantly reduced, because for every location or for every data, I could put it either here or there. And at the time of reading, I would simply compare which address tag was matched. And based on that, I give a hit and return the output from the memory to the processor. Questions?
Sir, I lost my connection, sir, actually. So how is the area increasing, sir, exactly? So,
The area is increasing because instead of one comparator, which was there in the direct map cache, now we have two comparators.
sir,
There is
but
also a mux involved there.
in direct map, we had many number of comparators in the previous image you have shown.
That was a fully associative one. Direct map only had one comparator. Direct map mein you could store any data
Yes.
only in one location. So only that location, only that line's tag you would compare.
Okay,
In
sir,
fully
sorry.
associative, any line could go anywhere. So you have to compare every location's tag, and that is where there are so many comparators. In set associative, if it is an n-way set associative, then any line can go into n different places, which are all operated in parallel. So now, if it is a two-way set associative memory, there are two comparators that have come into picture instead of one. If it was a four-way set associative memory, four comparators would have been there. Are you able to see this? Is this clear? So this is a mix of fully associative and direct mapped.
Hello, sir.
Yes.
Sir, I have a question here. Sir, address tag is not a unique value, no, sir, because multiple data blocks can have the same address tag, if I'm not wrong.
Why?
Sir, suppose if I have
Because the address tag is the address space of the total memory space that could be there. In fact, the physical memory would be smaller than that. Address tag is, it's a 32-bit address, which is the virtual memory space.
Sir, suppose if I have a case wherein the memory has memory is 32-bit word, whereas in the cache I have a cache line associated with 16 bits. Then in that case, the MSB of the address is stored in the cache tag. So at this point in time, both if I want to store this 32-bit from the memory into the cache, so I'll have two cache lines, which will be having the same address tag. No, sir.
Okay, so typically the scenario is the opposite, Ranjit. The scenario is that if the word is 32-bit wide, the cache that you would want to use is at least 32-bit wide, or let us say 64 or 96 or 128-bit wide. So more words are stored in the line than half word. Okay. If my cache is only 16-bit wide, my processor will have to be 16-bit only. Okay.
Yes, sir.
So tag is unique. Anything else?
Sir, in direct map cache, when we were talking about the conflict misses, you told one of the solution was to increase the cache size. So how will that
resolve
how
or reduce
is
the
the problem resolved?
Yeah. So let us say instead of 32 lines in your cache, you have 64 lines in your cache. So now what happens? Earlier there was so let us say the L2 cache memory is 1K big.
Okay.
So you gave address and because of 1K big आपकी L2 cache है यहाँ पे 32 lines हैं L2 cache में 1K lines हैं. So for every line in L1 cache, there could be 32 locations of L2 cache which would want to come there.
Hmm.
Now, let us say my L1 cache I have increased to 64 lines.
Acha, okay.
So now only 16 lines of the L2 cache would want to come there, come to every location. So the probability of a conflict reduces.
Okay, okay. Thank you, sir.
Okay, anything else? Okay. So which block should be replaced on a miss? See, for the direct map, it's very easy. There is only one location. If the address is matching, you have to simply replace that. However, it is a different answer when it is a slightly complex choice when you have a fully associative or a set associative memory. So experiments were done, and we see, particular data set, particular architecture, and particular program. Some experiments were done, and two different policies were compared. Random. We don't even check which address was used where, which set was being used last and everything, and you simply replace it. So we saw that, okay, if the associativity is 2-way, 4-way, or 8-way, there were different results of misses. So are you able to clearly observe a trend here that as you increase the number of ways, the total number of misses are reducing? And this is not just for random replacement policy. You will see this trend also for the least recently used replacement policy. This is intuitive. Are you able to see the intuition behind it? The intuition that we just discussed in the previous slides. Any doubts? You realize that this trend is in line with what we just discussed. Hello?
Yes, sir.
And the other trend that we were just talking about, that as you increase the cache size, what happens? Again, because now you can store much more data, the miss penalty reduces. Now, if you were using 8-way and a very big memory, you use whichever of the two algorithms, LRU or random. Doesn't make a difference. Same performance. But if you are resource constrained, then there could be some 10% difference between the two algorithms. So this is 5% plus 6%, and this is 5% minus 6%. So overall 12% gap between LRU and random. Is this clear? Are you able to see this? That LRU could be a better algorithm, but if you already have sufficient resources, then don't put in the energy to store which value was least recently or most recently used. You simply randomly replace, and it is good enough. Any questions?